up to the n mn rn square. I is equal to, its summation of I is equal to 1 to n mi into ri k square. For uniform body, the moment of inertia is also determined by the equation I is equal to integration of r square dm, and it is also given by I is equal to mk square, where k is radius of gyration. K is equal to under root of r1 square plus r2 square plus up to r square divided by n. It is also called root mean square radius of all point about which the body is rotating. Torque. It's also called moment of force. Means torque is given by R cross F or R cross F sine phi n cap. The direction of torque is perpendicular to the plane containing R and F. If we have only considered the magnitude, then torque is equal to R into F sine phi. If phi is equal to 0, torque is 0. If phi is equal to 90 degree, torque is equal to R into F, which is a maximum value. We have force is equal to mass into acceleration. That is, torque is also given by Rm into A, where A is equal to R into alpha, means torque equal to mr square alpha. For a system, total torque or net torque is given by T1 plus T2 up to Tn, which is also given by T is equal to I into alpha. Torque is also given by a rate of change of work done with respect to the displacement, or dW equal to torque into d theta. Condition for rotational equilibrium. Net torque tau is equal to 0. If no torque applied on a system, then body is said to be in the rotational equilibrium. For example, if you apply 2 torque on a body, T1 and T2, or tau1 and tau2, and under the effect of these two torque, the body is in the equilibrium, means the sum of the two torque is equal to 0. That is, both torque have the same magnitude acting in opposite direction. Again, work done by the torque, it can be given by dW equal to T into d theta. Power associated with torque is given by P is equal to rate of change of work done, which is given by T d theta divided by dt, or power is equal to torque dot angular velocity, which is omega. Application of torque. Net torque along alpha is always equal to I into alpha. Example. Motion of a body on an inclined plane. A body is placed on an inclined plane having mass m, weight acting vertically downward. Mg cos theta is acting opposite to the reaction force, whereas R is acting perpendicular to the contact plane. Friction force opposes the motion of a body, means it always acting opposite to the velocity. Mg sin theta acting along the plane. According to the Newton's second law, means for only translation motion, net force along A is equal to mass into acceleration. That is, net force mg sin theta along acceleration, friction force opposite to the acceleration, mg sin theta minus friction force is equal to mass into acceleration. Equation number 1. Again, for rotation, net torque due to friction force is equal to Fr into R, which is force into perpendicular distance. We have torque equal to I into alpha, which is equal to Fr into R. Fr, the friction force, value of the friction force is given by Ia upon R square. We have from equation 1 and 2, A is equal to G sin theta upon 1 plus I upon m into R square, where I is a moment of inertia of a body. It is different for a different body. For any body, we place the value of I in this equation, and we are able to determine the value of acceleration of a body which is moving down inclined plane. Energy in a rotational motion. Kinetic energy of a body in rotation motion is of two types: kinetic energy of translation plus kinetic energy of rotation. Means the total kinetic energy of a body is a sum of kinetic energy of translation plus rotation. Now the value of kinetic energy of translation is equal to half mv square, whereas the value of kinetic energy of rotation is equal to half I omega square. Means if we are talking about the total energy of a body in a rotational motion, it is always equal to the sum of potential energy plus kinetic energy of translation plus kinetic energy of rotation. That is mgh plus half mv square plus half I omega square. If you apply the